Welcome back, podcast 3 of this week. And guess what, guys? This is actually the final podcast of the week. Stoichiometry is, as I've said before, a really important concept. And I need you to be spending, yes, your time doing the podcast for sure, but really working through the questions in the assignment, working through them individually to actually understand it. Now, our last focus today is gas stoichiometry, because in the realm of gases, we have the ideal gas law, which allows us to look at how pressure, temperature, volume all relate to the amount of a gas. Ding, 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 amount, number of moles. So moving into this one, we are going to use, generally speaking, a rearrangement of the ideal gas law. Now, this is rearranged so that N, amount in moles, is by itself, but the familiar law to you is PV equals nRT, right? And then you can rearrange that as you need to look for the different variables, which you will be expected to do in the context of questions. Maybe you'll be looking for pressure, maybe you'll be looking for volume, etc., etc. Just a couple reminders to you with this, and I reviewed this, I don't think it was last week, the week before already, or maybe it was last week. Anyway, couple of review sets is that the volume has to be in liters, the pressure has to be in kilopascals, and the temperature has to be in Kelvin. So if you're given a temperature in degrees Celsius, you're going to have to add that 273.15 to the degrees Celsius in order to convert it properly to Kelvin. R, to remind you again, is that universal gas constant. On your formula sheet, hanging out right, where did it go? Ding, 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 right here. Okay, universal gas constant. So it's always available to you, and it will definitely be utilized with this section of the week's notes. Now, ultimately, in the context of this ideal gas law, the expectation is you'll still have questions that, of course, deal with mass, and you still potentially will have questions with a concentration. So be it, guys. It's just adding another tool to the toolbox. Steps. The great news is I'm not even going to spend a whole lot of time on the test, because you can rely on the exact same 4 steps we've already used for the other stoichiometry problems. Yay! Anytime you get to utilize an identical process, it makes life easier, and life being easier is always good. So of course, though, I cannot emphasize enough, begin with your balanced chemical equation. This never changes. What's going to change is that potentially you will now use another different formula related to gases to help you get to your end goal, whether that is volume, mass, pressure, etc. Okay, let's jump right into some questions, guys. First things first, notice that this question mentions a solution. That doesn't guarantee that right away you're dealing with solution stoichiometry. I'll show you what I mean. Reacts completely with 5 grams of zinc. Oh, this actually sounds like a familiar question. But notice the next part. What volume, still sounds like solution, ding, 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 hydrogen gas. If you see the word gas in the context of a question, your brain should start to think, this might be gas stoichiometry. There's 2 more hints here that guarantee it. A temperature is mentioned and a pressure. For sure then, you have to utilize the ideal gas law and, as I said, gas stoichiometry. So step 1 doesn't vary though. We need to do a balanced chemical reaction. Hydrochloric acid, we had this reaction previously, reacts with solid zinc to produce hydrogen gas and zinc chloride. Zinc chloride is an aqueous compound. Let's balance this thing out. We're going to have 2 hydrochloric acid. Everything else is 1, 1, 1. Nothing changes in terms of how we approach this. You still need to write down what are you given. In this case, it's 5.00 grams of zinc. And what is the whole purpose of the question? Well, the whole plan here is you need to try to figure out the volume of that hydrogen gas. That's what we're doing here. Now, what else do you know? Well, the question tells you, for example, 21 degrees Celsius is the temperature. Well, let's put that under. That relates to the gas. So 21 degrees Celsius, I need to take that 0.0 and add 273.15, and I will end up with a total of 294.15 Kelvin. Pressure is also given to you in the question. It is 99.6 kilopascals. R, the universal gas constant, is also a given. Okay. You don't have enough yet, though, to get volume, because if you don't have N, the number of moles, that ideal gas law isn't something that's usable. So let's go back to the zinc. Mass is a given, but don't forget about the molar mass. That's something that is always available to you as long as you know the chemical formula. 65.41 grams per mole straight off the periodic table. You bet there's enough info here now to get the number of moles of zinc. N equals mass over molar mass, 5.00 grams divided by 65.41 grams per mole. My grams will cancel out. We now have a number of moles of zinc. Don't round it. Unrounded values, that doesn't change. 0.0764 ... moles. Now, with a mole ratio, I can now relate this to the number of moles of hydrogen gas. So let's take that and do a comparison. My hydrogen gas, as compared to the zinc solid, is, in this situation, a 1-to-1 ratio. So 1 mole is 1 mole. Let's then get that to figure out the number of moles of hydrogen gas. X over 0.0764 ... moles. Same thing, cross multiply, divide. Do you see the pattern here, guys? We go through an identical stoichiometric process with each of these questions. Times it by the number of moles of my zinc, divide by 1 mole, and we will end up for our number of moles of H2 gas as an identical number, hence the 1-to-1 ratio, 0.0764 ... moles. Okay, now we're getting really close. Because we have the number of moles of hydrogen gas, we are now fully able to figure out what is our volume of that gas. So go back, think about the original ideal gas law equation, PV equals nRT. This needs to be arranged for volume. So divide by pressure on both sides. Volume equals nRT divided by pressure. Okay, start plugging in what you know. We just got that number of moles, 0.076 ... moles. Times R, yes, I want you to write out the whole thing. I know it's tedious, deal with it. 8.314 liters per kilopascal divided by moles times Kelvin. Units are important, hence you need them. Times by that temperature, 294.15 Kelvin. That entire portion divided by the pressure, 99.6 kilopascals. Everything ends up canceling out except for liters. So we're going to end up with an end answer with 3 sig digs of 1.88 liters. And there you have it. That is our volume of hydrogen gas. Once again, still stoichiometry, still comparing amounts with mole ratios, but now incorporating in the ideal gas law as one of the tools you have to figure out an amount in moles. One last example. Check out this one. We're going to have a sample of cyclopentane. Ding, 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 hydrocarbon. That should make you start thinking about the type of reaction. And sure enough, is burned. Burned completely, combustion. In the context of this reaction, we have oxygen gas, 125 liters of it. Ooh, and here's something you haven't seen for a while at SATP, Standard Ambient Temperature and Pressure. The whole point of this question is to figure out the mass of cyclopentane that got burnt. Okay, where do we start? Never sit there and go, I don't know what to do. No, you do know where to start. Balanced chemical equation. That's where we always start. So let's begin. C5H10 liquid burns, hence combustion, presence of O2 gas. Produces, it is a hydrocarbon, which means it will always produce with complete combustion carbon dioxide gas and water vapor. Not water liquid, water vapor. Yes, they're different. Yes, it's important. Keep going. The whole point of this question is what mass of that cyclopentane is going to be consumed. In other words, what is the mass of this thing? We know the volume is 125 liters. At this first glance, it looks like we know next to nothing. But I don't want you to forget this whole concept of an SATP. Like I said, it's been a while since we've talked about that. Go to your data sheet and think back, way back. Here's SATP. So that actually gives you a temperature and a pressure to utilize. If you have, hint, hint, a different question that talks about STP, that's standard conditions, then it's a different temperature and a different pressure that you're working with. Okay, back to the question. Given then, from your data sheet that it's SATP, you now know that you're dealing with a temperature of 298.15 Kelvin, and you now know that you're dealing with a pressure of 100.000 kilopascals. R, of course, you've got. Look at what we have here. We have volume, temperature, pressure, and R. We have absolutely everything we need to figure out the number of moles. Yay! Because we need that. There's not nearly enough information for cyclopentane. We're looking for the mass. Sure, we've got the molar mass calculated out, 70.15 grams per mole. I got that by going 5 times 12.01 plus 10 times 1.01. But it's still not enough to get moles. So go to oxygen. Rearrange PV equals nRT. You're going to get N equal to PV over RT. Plug in what you've got. Pressure is 100.000 kilopascals. Volume was the question, 125 liters. That whole thing divided by 8.314 liters times kilopascals over mole Kelvin, multiplied by 298.15 Kelvin. Now don't forget, please, you need to take the entire top and divide by the entire bottom, or you're going to end up with incorrect numbers. When we cancel out all of our different units, it wonderfully works out that moles is going to be left. And in the end, the number of moles of oxygen gas, unrounded, is equal to 5.04 ... moles. Well, now what? We've got the number of moles of oxygen, yay! But we need to relate that to the number of moles of cyclopentane. Well, guys, not going to happen unless you balance. This is so often what people forget, and they'll just go 1 to 1, we're done. No, look back. We have a combustion reaction. Tougher to balance. Remember the trick I told you. Try multiplying it by 2 right away. You can reduce in the end if you need to. That puts us up to 10 carbons, so I can put a 10 here. Don't touch the oxygen yet. Go to hydrogen. We got 20 hydrogen reacting, so I need the equivalent of 20 produced. 10 times 2 will do that. Now, last, oxygen. I have with my water 10 oxygens. With my carbon dioxide, I got 20. 2 times 10. 20 plus 10 is 30, so I'm going to put a 15 in front of this O2. Look at those numbers, 2, 15, 10, 10. I can't reduce that. This thing's balanced. And from a mole ratio perspective, well, it's a noticeable one. We're comparing 15 oxygens to 2 cyclopentanes, right? Take the time. Yes, some moles or ratios are easy, and some are harder. So comparing them to what we are trying to find out, the C5H10, compared to what we know, the oxygen, and write down the ratio, it is a 2 mole ratio compared to a 15 mole, right? 2 to 15 equals, here's our unknown on top. The value we just found from the ideal gas law is 5.04 ... moles of oxygen gas. Cross multiply and divide. X is equal to 2 moles times 5.04 ... moles divided by 15 moles. In the end, that means the number of moles of cyclopentane is equal to 0.6723 ... moles. Good news, if I've got the number of moles of that cyclopentane, then I have everything that I need from this to figure out the mass. So I'm going to leap back over here again, and I'm going to use that old formula. Mass is equal to the number of moles times the molar mass. Number of moles we just found out, 0.6723 0.6723 moles times by the molar mass, 70.15 grams per mole, cancel out moles, mass of that beautiful cyclopentane, 3 sig digs, 47.2 grams. And there you have it. Done and done. We have now just solved a gas stoichiometry question. Homework-wise, guys, the last questions in your assignment related to gas stoichiometry are these three, 7, 8, and 9. Now, I'll be honest with you, I originally had 4 more questions on this assignment that were a mix mash, and I ended up taking them off because I felt like it was a little bit much. If you decide that you want some additional questions, let me know. I am going to attach an extra sheet to the notes, and I'll have an answer key for it too that have some of these additional questions, right? Stoichiometry practice. So these are the questions on it. They're fully, completely answered in the notes. You can check them out, but back to here, if you finish up to number 9 in the assignment, you've now completed week 9 assignment. Good luck, guys. Do your best, please. Ask questions as you have it. Talk to you soon. Take care as always.